Welcome to next lesson in relativity. Today we are going to discuss the variation of mass with velocity. Relativistic mechanics അനുസരിച്ച് ഒരു പാർട്ടിക്കിളിൻ്റെ മാസ് എന്നുള്ളത് അതിൻ്റെ വെലോസിറ്റി ചേഞ്ച് ചെയ്തതിനനുസരിച്ച് ചേഞ്ച് ചെയ്യുന്നതായിട്ട് വേരി ചെയ്യുന്നതായിട്ട് കാണാൻ പറ്റുന്നുണ്ടാവും. This is called variation of mass with velocity. So we are going to discuss that concept. We will start from the assumption that law of conservation of momentum, it is a fundamental law in physics. So we assume that it holds correct even at relativistic speeds. And we consider two frames of reference S and S dash. The frame S is called a lab frame, and there is another frame S dash which is moving with a velocity v along the x direction with respect to the frame S. ഇവിടെ രണ്ടാമത്തെ ഫ്രെയിം എസ് ഡാഷ് എന്നുള്ള ഫ്രെയിം ഒന്നാമത്തെ ഫ്രെയിമിൽ നിന്ന് വി വെലോസിറ്റിയിൽ പോസിറ്റീവ് എക്സ് ഡയറക്ഷനിൽ മൂവ് ചെയ്തുകൊണ്ടിരിക്കുകയാണ്. Now we consider a particle which has a rest mass m0. Rest mass means it is the mass of the particle measured by an observer which is at rest with respect to the particle. ഒരു പാർട്ടിക്കിളിന് റെസ്റ്റിൽ ഉള്ള മാസിന് പറയുന്ന പേരാണ് റെസ്റ്റ് മാസ്, അല്ലെങ്കിൽ മറ്റൊരു പേര് ഇറ്റ് ഈസ് കാൾഡ് പ്രോപ്പർ മാസ് ഓഫ് ദ പാർട്ടിക്കിൾ. ആൻഡ് വി ആർ ഗോയിങ് ടു ഡിഫൈൻ ടു ടൈം ഇൻ്റർവെൽസ്. ലെറ്റ് ഡെൽറ്റ ടി ബി ദ ടൈം ഇൻ്റർവെൽ മെഷേർഡ് ബൈ ദ ലാബ് ക്ലോക്ക്. ആൻഡ് ലാബ് ക്ലോക്ക് എന്ന് പറയുമ്പോൾ ദ പാർട്ടിക്കിൾ വിൽ ബി മൂവിങ് ഇൻ ദ ലാബ് ഫ്രെയിം. ലാബ് ഫ്രെയിമിൽ പാർട്ടിക്കിൾ മൂവ് ചെയ്തുകൊണ്ടിരിക്കുകയാണ്. സോ this time interval measured is not the proper time interval. Proper time എന്നുള്ളത് it is delta tau. That is time interval measured by a clock moving with the particle. ആ പാർട്ടിക്കിളിൻ്റെ കൂടെ മൂവ് ചെയ്യുന്ന ഒരു ക്ലോക്ക് മെഷർ ചെയ്യുന്ന ടൈമാണ് ഡെൽറ്റ ടോ എന്നുള്ളത്. ഇറ്റ് ഈസ് കാൾഡ് പ്രോപ്പർ ടൈം. ആൻഡ് ഫ്രം ദ ടൈം ഡയലേഷൻ വി നോ ദാറ്റ് the proper time interval delta tau equal to delta t into root of 1 minus v square by c square. This is the proper relation connecting the proper time delta tau and the time measured by the lab frame delta t or S frame എന്ന് പറയാം. Now from the Lorentz transformation we can see that the displacement along the y direction will be same for all inertial frames because the particle is moving along the x direction. So there is change only in the x coordinate. X and x dash will be different, but y and y dash will be same. So delta y എന്നുള്ളത് എസ് ഫ്രെയിമിലും എസ് ഡാഷ് ഫ്രെയിമിലും സെയിം ആയിരിക്കും. ഡെൽറ്റ വൈ സെയിം ആണെങ്കിലും ദ ടൈം ഡെൽറ്റ ടി ഓർ ഡെൽറ്റ ടോ ദേ ആർ ഡിഫറെൻറ്റ് ഇൻ ടു ഫ്രെയിംസ്. Now we consider the momentum of the particle along the y direction in the s dash. എസ് ഡാഷ് ഫ്രെയിമിലുള്ള പാർട്ടിക്കിളിൻ്റെ മൊമെൻറ്റം എന്നുള്ളത് പി വൈ ഈസ് ഈക്വൽ ടു m0, that is the mass measured with respect to an observer who is at rest with respect to the particle. ഈ പാർട്ടിക്കിൾ റെസ്റ്റിൽ നിൽക്കുന്ന സമയത്തുള്ള മാസാണ് m0 എന്നുള്ളത്. സോ പി വൈ ഈസ് ഈക്വൽ ടു m0 ഇൻറ്റു ഡെൽറ്റ വൈ ബൈ ഡെൽറ്റ ടോ. ദിസ് ഇസ് കാൾഡ് ദ മൊമെൻറ്റം ഇൻ ദി S dash frame, that is equal to P m0 into delta y by delta t into delta t by delta tau എന്ന് പറയാം. That is equal to m0. This delta y is the displacement along the y direction. It will be same in both the S and the S dash frame, and delta t is the time interval measured in the lab frame. So delta y by delta t is the velocity along the y direction in the lab frame. It can be called as Vy. So it is m0 Vy into this delta t by delta tau. From this relation it becomes 1 by root of 1 minus v square by c square, where Vy is the y component of velocity of the particle in the lab frame. Therefore we can write the y component of momentum Py is equal to m0 by root of 1 minus v square by c square into Vy. So this can be written as Py is equal to some mass m into Vy. Here in the place of the mass m there comes a quantity m0 by root of 1 minus v square by c square. So this is the observed mass with respect to the lab frame. So this observed mass with respect to the lab frame is different from the rest mass m0 of the particle. With respect to the lab frame, the particle is moving with a velocity v. So the mass of the particle as observed from the lab frame is different from the rest mass of the particle. So m is equal to m0 by root of 1 minus v square by c square represents the variation of mass m with respect to the velocity v of the particle. This is called the relativistic variation of mass with velocity. And by a special case, if the velocity of the particle is equal to 0, if v is equal to 0, we get m is equal to m0. That is, if the particle is not moving at all, we will get the proper mass of the particle, or called the rest mass of the particle. Now, there are experimental verification for the variation of mass. Mainly it is verified for the case of subatomic particles. One of the verification came from the experiments in which the E by M of electrons were measured. And it was found that by a scientist, Butcherer, he found that E by M of fast moving electrons was smaller than that of slow moving electrons. Because E is constant. It is a constant. It is independent of the velocity. Charge of the particle is a constant of the electron. And the m is the mass of the electron. It will be more for fast moving electrons. As velocity increases, the mass also increases. So for fast moving electrons, the E by m will be small, and it is experimentally verified. Another important consequence of this variation of mass with velocity is the ultimate speed of particles is the velocity of light. Because if we draw a variation of graph with the mass along y-axis and velocity of the particle along the x-axis, we will get a graph like this. For smaller velocities, the mass will be almost equal to the rest mass of the particle m0. But as velocity increases, we can see that this m0 by root of 1 minus v square by c square also increases. And when velocity v approaches the velocity of light c, this quantity v by c approaches 1, and 1 minus 1 approaches 0, and the relativistic mass approaches infinity. So as mass approaches infinity, any force given to accelerate the particle will increase the mass of the particle, and velocity remains almost constant near c. So we can say that no material particle can attain the speed of light. Material means particles having a definite mass. Electron is having a definite mass. Proton is having a definite mass. So all these particles, whether they are light particle or massive particle, if it has a definite mass, if there is a non-zero rest mass, it cannot attain the speed of light. It can go up to the speed of light, but the speed of light is not attainable by the material particles. But it can be attained by particles having rest mass equal to 0. For example, photon. In the case of light photon, the rest mass is equal to 0. Therefore, their speed is equal to the speed of light. So, particles having a rest mass cannot attain the speed of light, or we can say the ultimate speed of particles is the speed of light. Ultimate means it can never reach the speed of light, but it can approach a velocity very near to the speed of light, but it will never reach the speed of light. Now one more last concept, it is the relativistic momentum. In relativistic mechanics, the momentum of the particle is defined as P is equal to mv, where m is the relativistic mass of the particle and v is the velocity observed in that frame. So here the relativistic mass will be equal to the mass, that is m0 by root of 1 minus v square by c square. So this expression m0 v by root of 1 minus v square by c square represents the relativistic momentum, and we cannot use the classical momentum as p equal to m0 v. Here relativistic momentum is to be used. This m is called the relativistic mass, and m0 is called the rest mass of the particle. So thank you for watching this video.